Okay, so where do we start on the pizza problem? Anybody?
Uh, Free body.
Yeah, free body.
Okay. So we've got the free body diagram. Okay, so what's the so here's the tray, right? And then you've got a pizza sitting on top of it. So what possible forces could we have on the pizza?
Gravity.
Gravity, okay.
And
What
then
else?
there's
Sorry, what was that?
friction
There's
between
friction.
the
Okay.
tray and pizza.
Yep, there's definitely friction.
A
So which
normal
way
force.
is the friction friction going?
It'd be to the left because the pizza was jerked to the right.
Okay, so the waiter jerks the tray to the right. Okay, so we know the tray has an acceleration, right? And we want to figure out what happens or what the coefficient of friction is so that the pizza moves with it, right?
Oh shoot.
So the pizza is going to move that way, right? So which way does the friction force need to be?
To the left, right?
If it's okay, so then what's making the pizza accelerate? Okay, there's a normal force, right? That's from the tray.
This
Okay.
is like the plane. This is like the plane problem, and
Like the supplies in the back of the plane.
thing.
Yeah. So remember, this is static friction. Static friction can go in whatever direction it needs to keep two objects from moving relative to each other, right? So if the tray is accelerating this way and we want the pizza to accelerate with it, then the friction force better be this way, right? Because if the friction force were backwards, then the acceleration of the pizza would be backwards. There'd be no force to make it accelerate forward, which is what we need to have happen over here, right?
So it's like before we got. So it's like, is it wouldn't like a car burn, like doesn't burn out? It wants to go forward. The friction is it's
Right.
going forward. Like the
Exactly.
acceleration is forward, so the friction is also forward.
Yes. So every time you don't squeal your tires when you drive a car and you go forward, right? You accelerate forward. That is because of a friction force pushing you forward, right?
Static friction force, right?
This is the tricky thing because this is a static friction force. Static friction can be in whatever direction. It can be in the direction of motion, backwards, right? The only thing static friction wants to do is it wants to keep these two objects moving with each other, right? Not moving relative to each other. Okay, so here's our free body diagram. Now what do we do?
You like draw like the forces. Write them out.
Okay, so we've got our
Like how we
forces,
do
right? So now we can write Newton's
G.
second law. Newton's second law just says our acceleration has got to be equal to the sum of our forces divided by mass, which if I just add my forces, okay, I've got a normal force and a gravitational force and a friction force divided by mass, okay? Now I need to figure out how to split them up into components, right? Because this acceleration, the acceleration we need, right, is going to be, well, 5 meters per second to the left or to the right and 0 up or down, right? So let's split it up. We've got an X component over here. We've got a Y component over here. Well, in the X direction, we know our acceleration. I'm just going to call it AX, right? And it can only be caused by the friction force because normal and gravity are both in the wrong direction, right? They're in the Y. So all we've got here is a friction force divided by mass. Okay? That means we can tell you how much friction you need to have, right? This means if we use this equation, we know that the friction force has just got to be the mass of the pizza times the acceleration. Okay, so we know how much friction force you need, but that doesn't tell us what we need to know, which is the coefficient of static friction. Okay, so let's come over here to the Y components, right? The Y component, there's no acceleration, so I can just write 0. The sum of my forces, well, I've got a normal force going up, and I've got a gravitational force going down. If I multiply through by the mass, I get that and move the gravity to the other side, I get that my normal force is just equal to the weight. So my normal force is just mass times gravity, right? Times 9.8. Okay, now I can come back over here. How do I relate these two? Friction force and normal force.
The friction force is the normal force times nu.
Right. So I know that my friction force is that coefficient times my normal force, which means that if I take this equation and bring it down here and combine it with this equation, I get that I get mu mg equals m times the acceleration, right? The mass cancels on both sides. So it turns out it doesn't matter how heavy the pizza is. And I get that my coefficient has to be my acceleration divided by gravity, right? So that coefficient has to be, well, it's approximately 5 divided by 10, or in other words, about a half for the pizza to stay on the tray. Okay, how are we feeling?
Better.
Good. It's a little bit counterintuitive, right? That the result doesn't depend on the mass of the pizza. But it turns out that's because our model for friction assumes that the friction force is just proportional to the normal force. Now, it turns out that's actually true, but the coefficient you're going to get is going to change as you get more pizza. Why? If I stack more pizza on there, if I get a deep dish pizza versus a thin crust, why would the coefficient change?
You got more normal force.
Well, that'll give you more friction force, right? But
Yeah.
I'm saying not just the normal force is going to change. If I put more pizza on there, the coefficient is going to change too. Why do you think?
The weight.
Well, that's just the balancing the normal force, right? What does the coefficient have to do with? The coefficient is not having to do with the weight at all. The coefficient's having to do with what? This mu thing. What is this mu taking the place of? What's actually happening between the pizza and the tray?
They're rubbing together, the friction. Like,
Right. So it's the surface, right, of the pizza is interacting with the surface of the tray. So if I stack more pizza on there, what happens to the bottom of the pizza? How is a thin crust pizza different, the bottom of the crust different on a thin crust pizza than like a pan pizza?
get pushed into it more? Or?
Right. And so instead of having this like light, fluffy thing sitting on top of it, right, you're actually smashing the dough down. And so you're actually going to get a different coefficient of friction because you've changed one of the surfaces, right? You've changed the way the pizza crust is simply by making more stuff go on top of it, right? You've smashed it down. You've made it more of like a, you've changed the way it's contacting the thing, right? So remember these coefficients, the point I'm trying to make here is that these coefficients, they're hiding a lot of stuff, right? They're hiding all the details about the two surfaces and how they interact with each other. Okay, Davey, you ready to tell us all about shooting a ball out of a tube?
Yeah.
All right, let me come back over here. Put this thing up. All right, so what's the best way to do this? Do you want to describe what you're doing? Do you want to, like, can you write it down and share it?
I can probably do that.
Whatever works the best. So we're talking about this problem in the top left. The ball of a mass 100 grams is accelerated upwards through a 1 meter long tube, okay, by compressed air. The ball experiences a constant upward force of 18 newtons from the compressed air while it's in the tube. Then it is in free fall after that. How far above the top of the tube does the ball travel? Okay, so I'm going to stop sharing this, and that way we can all see Davey and what he's going to do for us. So tell us his tale.
Professor Nelson, I think I have a camera.
Okay,
Can you
that'll
see my
work.
screen?
Yeah, I can see it.
Okay, so I started with writing everything down. So the mass of the ball is 0.1 kilos, which is 100 grams. And then you have a constant force of 18 newtons. And so the ball travels for a meter in the tube, and it accelerates with the 18 newtons. And so force is mass times acceleration. And then so acceleration is the force divided by the mass. And so 18 newtons divided by 0.1 kilos, it's 180 meters per second squared. And then from there, you get that the position equation for just when the ball's in the tube is 90t squared, because your velocity initial is 0, and then your position initial is 0, if that's how you set up your coordinate plane. And then from there, you can get that t is like the time that it's in the tube accelerating is the square root of 1 divided by 90. And then from there, I plug that into the velocity equation. And then I got that its speed coming out of the tube is 18.97 meters per second. And then from there, I put it into the position equation from when it comes out of the tube, where the acceleration is minus 9.8 meters per second squared. And then from there, I got that I put it into Desmos, and I got that it peaks at 19.36 meters above the tube. And then you subtract 1 or 19.36 meters above where it started. And you subtract 1 because that's how big the tube is. And then so it peaks 18.36 meters above the tube.
All right, very nice. Questions? Okay, so somebody take the sort of cartoon sketch here. How did he do this? Oh, come on. Okay, my internet's back. All right. How did he do this problem?
He first
Do you
found
mind if I-
acceleration.
Okay, so he used Newton's second law, right, to get the acceleration. Sorry, there was another, somebody else said something there.
Oh, I was just gonna ask if I could the next one.
Sure. Okay, so
Thanks.
on this one, so the first thing he did was he looked at this problem and he saw it as a Newton's second law problem, right? And so he set up Newton's second law. He figured out what the acceleration of the ball was in the tube. And once he knew the acceleration of the ball, he could figure out the velocity of the ball when it came out of the tube. And now it's just a kinematics problem, right? How else could you have done this problem?
I just want to ask. He figured out acceleration through knowing the force and the mass, right?
Right. Yeah. So he just wrote Newton's second law, right? He said, you know, the mass of the ball, he knows the force on the ball, right? The ball gets a constant upward force of 18 newtons. So you can figure out the acceleration of the ball. Once you have acceleration, you integrate it in time and you've got velocity. Once he did that, he could figure out how long he could integrate it again to figure out how its position. Once he did that, he could figure out the time it took for the ball to get to the top of the tube. And once he had that, then he could go back and figure out the velocity of the ball at the top of the tube. And then it was just a kinematics problem, right? Okay, how else could you have done this problem? So did anybody notice when he was solving this thing that he spent a lot of his time trying to figure out the time it took when different things happened? Even though we didn't actually care the time anywhere, he just had to figure it out in order to figure out the velocity or figure out the position.
You can use energy.
Yeah, you can use energy. So let's not do the problem, but I want to just sketch it real quick for you. With how you would do this problem using energy. So the first part of the problem, right? You've got the tube, right? And the ball's in the tube. And this is a 1 meter tube, okay? So we can use the work kinetic energy theorem here, right? We can figure out how much work is done on the ball because we know the force and the distance. And we can say that that work is just equal to the change in kinetic energy, which is final minus initial. There is no initial kinetic energy. So that work is just going to be 1/2 mv squared when it gets out of the tube. Okay, once it's out of the tube, then what can we do? So sort of
Well,
phase
we know
two.
the mass.
We do know the mass.
Is
So
it
what go ahead.
is it just 1/2 mv initial squared because final is 0? It kind of
Yeah.
comes to a stop.
So if we
Top.
do energy, right? The energy down here is just 1/2 mv squared. There's no kinetic energy up here. So where did the energy go?
Why is the energy where does it come to a stop?
At the top, right? It comes to a stop at its highest point, right? For a brief moment at that highest point, it has no velocity. So what kind of energy does it have up here?
Potential energy.
Right. So up here, it's got mgh. Okay. And we can even make our lives easier by realizing that this 1/2, so this statement right here is just going to come, what's going to come from here is mgh equals 1/2 mv squared. And we can even make our lives easier by realizing that and that are the same. So that's just the same as the work. Which means if I take this whole thing down here, I get that mgh is the force times the distance. Which doesn't require us to use Desmos to solve a quadratic. We could do it.
How did you go from? How'd you get mgh equals force times distance?
Because mgh is 1/2 mv squared, right? That's just saying that the kinetic energy at the bottom turned into potential energy at the top. Well, I already figured out down here using the work kinetic energy theorem that the work done is just equal to the change in kinetic energy, which is just 1/2 mv squared. So that means I can cut the 1/2 mv squared out entirely and just say mgh is equal to the work.
Times the distance.
Yep. Well, the force times the distance. Yeah.
Yeah.
Okay, good. All right. Lucas, you were up next.
Thank you.
Which one do you want to do?
So let me try to get it on my screen. It's the one with a penny dropped off a skyscraper. It's on the 6th slide, bottom left.
All right. There you go. Okay, so let me just share the screen real quick so people can see the problem. So it's this problem right here on the bottom left. You've probably heard the tale that if you drop a penny off a skyscraper, it can kill someone. The Empire State Building is 381 meters tall. If the penny was in free fall all the way down, how fast would it be going when it hit the ground? All right, I'm going to stop sharing my screen and tell us a tale, sir.
I wrote it out, but I don't know if it'll really work at all to show it. Does it even appear correctly, or does it appear backward? Or is it just unreadable?
I can read it.
Looks normal.
Oh, okay, that's good. So let's see if I can try to explain it while showing it. So I use the position and velocity equations we learned toward the beginning of the course. And when using the position equation, you're able to get rid of the initial position because you'll just call it 0, and you know it's not moving, it's just dropped when it starts. So then it's just position is 1/2 gt squared, and I just made g positive since that's the direction it's going. I found that easier to think about. So then it gets rearranged. So t equals the square root of the distance times 1/2 g. So the time falling is 8.8 seconds. And then that's what we needed for the velocity equation here. So the initial velocity is 0, so it's just g times t, so 9.8 times 8.8 we got before, and the final velocity is 86.4 meters per second.
Great. Questions?
Could you hold that up again?
Yeah, sure. Now maybe I can do it more stably. There we go.
Okay, thank you.
Sure.
Okay, so how did he do it?
He found the time using the position equation. And then using that, he found the velocity, right?
Yeah, so he treated this as a kinematics problem. And it is. You could do this with a kinematics problem. How else could you do it?
Could do energy again.
You could do energy again, right? And I'll just give the quick sketch here, right? So here's your skyscraper. Up here, what kind of energy do you have?
Potential.
Potential, right? So that's assuming we put H, the zero of potential energy at the bottom, which makes sense. Okay, what kind of energy do you have down here?
Kinetic.
Kinetic. Which means that I can just set these two equal and solve the thing. Which, if I do that, I get mgh equals 1/2 mv squared. I can cancel the m's, and I get that the velocity is the square root of 2gh. Lucas, do you mind holding your paper back up?
No, sure. I'm surprised that this actually works.
So if you'll notice, his answer was, for the time, was the height, the square root of the height divided by 1/2, which is the same as multiplying by 2, divided by g. But then to get the velocity, he had to multiply that number by g again, which means what he had was the exact same thing that I did. Square root of 2gh. Can everybody see that?
Yes.
Great. So what's the difference here? Either one will give you the right answer,
He had to solve for time.
but he had to solve for time, right? So it was slightly more complicated. So really, when we talk about energy, there are very few problems that we can't do some other way, right? That require us to use energy. The real advantage to energy is that it often allows us to do things in a much quicker way because we don't have to worry about time. When we talk about energy, we don't have to worry about time. Now, that shortcut only works if we don't have to worry about time. If we do have to worry about time, well, then we're just going to have to go back and do things with, with forces and accelerations and kinematics and all that jazz. Okay, well, good job, Lucas. All right, what's next? What do you guys want to do next? Let me share my screen again. Okay, so let's see. We've done the penny on the skyscraper. Sorry, somebody was saying something.
On slide 6, the bottom right one.
The bottom right one, the metal ball.
Yeah.
You want to do that?
I mean, I didn't think I could do it, but I thought you. if we
Oh,
were
you
gonna
want me to do it? Ah, okay, I can do it. Luckily, I wrote all these, so I know. Okay, so we're talking about this one in the bottom right. The metal ball of mass m is hanging from a spring with a spring constant k and bouncing up and down. The highest point the mass reaches, which is also where the spring is unstretched, is distance h above its lowest point. Write a statement of conservation of energy for this system and use it to find the ball's velocity as a function of its position. Okay, so this is a little bit complicated. So let's start off with just the first thing. Write a statement of conservation of energy for this system. Okay, what's the first thing we want to do here?
Do we want to figure out like the energies it has? Like,
Right. So let's draw a picture. So basically what we're saying here is we've got a spring and we've got some mass, right? A ball, but I drew it as a cube, whatever, right? And it has mass m and the spring has spring constant k. And we know
can't
that
see your screen.
Sorry, what was that?
you can.
Oh,
can't see your screen.
right. I'm still sharing the thing. Okay. There we go. How about that? Good?
Yeah, except it's
All right.
blurry right now.
Hopefully it comes into focus here in a moment. All right, come on, camera. Woohoo. My goodness, this camera's not playing nicely today. There we go. Okay, so we've got a spring constant K, mass M. It's bouncing up and down, right? And what the problem says is that the highest point it gets to, right, is where the spring is unstretched, okay? So the highest point's up here, the lowest point's down here, and we said the distance between them is h, and up here, the spring is unstretched. Ah, sorry, that got small. I didn't leave myself enough space there. Okay, so we want to write a conservation of energy statement. So what energies do we have going on here?
We have
Well, we've got gravitational potential energy, right? So let's look about the top versus somewhere in the middle. Okay? What energy do we have at the top? Well, I said gravitational potential, right? Where do I want to put the 0 of my gravitational potential energy? Remember,
Is it
there's
in the
no
spring,
wrong
like-
answers, but there are some answers that are more helpful than others.
is it when the spring has like coiled like back already after bouncing?
You mean like when it's unstretched here? We could put our 0 of potential energy right there, right? We could say, I'm going to put the 0 of my potential energy right there, okay? In this problem, it might also make sense to put it at the bottom, but it's actually going to be nice to put it here at the top because of what we have to do with the spring potential energy, which we'll get to in a second. So at the top, we have 0 gravitational potential energy. Okay, I already said the other type of energy we have to think about is the spring potential energy. What's the spring potential energy here at the top? So the problem said that at the highest point is also where the spring is unstretched. So what does that mean for the potential energy of the spring if the spring is unstretched?
There's no energy in it.
Right. So it's also our 0 of our spring potential energy. Okay. And how about the kinetic energy? That's our third type of energy that we have to worry about. What's the kinetic energy at the top? All right, what do we think?
Wouldn't it be 0, like you said?
Yes, because it's not moving. So there's no energy at the top. Is that okay? Can I do that? Can I have 0 energy? Sure, right? Because this gravitational potential energy is arbitrary. I could have put the 0 of gravitational potential energy down here, and then we would have some. But 0 is a perfectly acceptable option for the total energy. Okay. Okay, now let's pick a spot in the middle, just any old spot, right? Some distance between the top and the bottom. And I'm going to call that spot Y, right? So Y could go from 0 up at the top to -h down at the bottom. So what's my gravitational potential energy at that spot that I just made up? Well, gravitational potential energy is just mgh, right? So mass times gravity times the height. But the height relative to where?
to the 0 mark. So it's going to be negative h.
Yeah, so we're not all the way at the bottom. So it's going to be negative mgy, right? Because y is going from 0 to h. So as you change y, right, you just go up and down. Okay, how about our spring potential energy? What's that going to be? Well, first of all, is it going to be positive or negative? Our gravitational potential energy is going to be negative. How about our spring? Anybody remember the formula for spring potential energy?
Kx.
Ah, that's the force, right? So if we want the potential energy, we've got to do an integral on that thing. What we end up with is 1/2 k, and then what's x that you just said? When you said kx, what was x?
Distance stretched.
Yeah, the distance it was stretched, okay? So in this case, our spring is going to be the distance we've stretched the spring over here, right? Which we just called y. So it's just going to be 1/2 k y squared. Now, it's positive because it turns out there is the spring potential energy is always positive or 0, but it's never negative because it's always relative to the unstretched length of the spring. And if I compress the spring, right, if I move y up here, that square is just going to take care of the negative, and I'm still going to get a positive number. Okay, how about our kinetic energy somewhere in the middle? Are we going to have some kinetic energy somewhere in the middle?
Yes.
Yes. So we're just going to have 1/2 mv squared. Okay, conservation of energy says I can add all these up and make them equal to the sum of all those. So if I write that out, I get 0 equals negative mgy plus 1/2 ky squared plus 1/2 mv squared. And there is my statement of conservation of energy. Okay. Energy at the top is equal to energy somewhere else. Okay. If I did this all the way at the bottom, right? We're down here at where y is h. Well, this would be 0, right? My velocity would be 0, but these guys wouldn't. But they'd have to add up to 0 because that's what conservation of energy says. So the second part of the question asked for the ball's velocity as a function of its position. Okay, well, I can do that. That means I need to solve for velocity. So let's move velocity to the other side. I get negative 1/2 mv squared is equal to negative mgy plus 1/2 ky squared, right? I divide through by negative 1/2 m. I get v squared is 2gy minus ky squared over m. And now I just take the square root. So my velocity as a function of position is just 2gy minus ky squared over m. Okay? So it's a mess, but but okay, right? Whatever. That's just what it looks like. So there's the other part of my question. There is my velocity as a function of position. which is kind of fun, right? I know if you tell me where you want to know what the pendulum's or the mass's velocity is, I can tell you what the velocity is if you give me a location. Okay? Which is kind of fun. Okay, questions?
How is it a like position? How is that affecting it? Oh, I see.
So position here is y, right?
Okay.
So
Yeah,
as you
okay.
increase y, right, as you move, as you move, as the mass moves downward, y gets bigger, right? And so this term gets bigger, this term gets smaller, and eventually they catch up with each other. Let's plot this thing. I think it'd be useful to plot it. So let me come over here, and let me just pull up Desmos real quick. Oh, that's not what I want. I want Desmos. Apparently I typed something in wrong. I ended up getting something weird. Okay, let me share this over here. Where do we go? There we go. Okay, and my internet is lagging painfully. So apparently Desmos has taken its time to load.
What
Well,
about
maybe
that thing that they sent you? That
What was
internet
that?
thing that they sent you from the school? The
Yeah,
thing that they
that's what
sent
I'm
from the
using
school,
right
is it
now.
any good?
This
The
is the new
internet?
and improved version. All right, so our velocity was equal to v equals the square root. I can get the square root by just doing 1/2 and then up there of 2 times g, which is 9.8, times y minus k, which we didn't define, but I don't know. Let's pick a k. I don't know, 5 times y squared divided by our mass, which we didn't pick either, but let's say it's 1 kilogram. And we're going to get something that looks like this. Okay, what is it doing? Well, it's because of the way I chose my variables. Desmos always assumes that y goes on the y-axis and whatever else you have goes on the x-axis. So this graph is kind of tipped over. I could change this if I made it y over here and x over there, right? So now my x-axis is position and my y-axis is velocity. So what happens here? Well, I drop the mass. I drop the mass and the velocity goes up until it reaches some point, and then it starts slowing down, and eventually it stops, and then it bounces the other way, right? And comes back this way. So what you have here is a complicated system, right? This would be actually a very difficult system to do with Newton's second law. We will do this with Newton's second law, but not until the end of the semester. But with energy, we can use it to get a relationship between velocity and position without having to do all of the messy calculus and algebra that we would have to do to go through Newton's second law. All right. Questions? How are we feeling? Okay, you guys want to do one more, or you guys had enough for today?
Let's do one more.
Do one more.
I
All
wanted to give
right.
it a try to one, but haven't had the chance to actually even do it because we've just been looking at the stuff, the problems.
All right. Which one do we want here?
Can I present a problem?
Sure.
Or
Which
I'm
one do
gonna
you
share
want?
my screen. It's on the second page. A car of mass 1,000 kilograms traveling at 30 meters per second needs to stop in less than 10 meters.
Okay. I'll stop sharing my slide and you go ahead.
It's not letting me share my screen.
Okay, that's me. I have to, they changed the settings here. Okay, you should be able to share now. Is it working?
Yeah, I just have to download something real quick. So it's at the bottom of the screen, it looks like.
Cool.
So I used work and kinetic energy for this. So work is equal to the change in kinetic energy, and it's also equal to force times the change in distance. So I equated those by setting them together. Force times change in distance is equal to the change in kinetic energy. So force is equal to the change in kinetic energy over the change in distance. And this right here gets zeroed. That right there gets zeroed out. So then force is just equal to negative 1/2 mv squared over the change in distance. I'm plugging everything in, I get negative 45,000 newtons.
All right, questions? Okay, how do you do it? Well, let me put it this way. How could he have done this? A month ago or 2 months ago, you guys would have looked at this problem and done what?
Kinematics.
Kinematics, right? And to do that, you would have had to figure out how much time it took to stop. And then you would have had to plug that back in to figure out the force needed, right? But instead, he just went straight to work kinetic energy, right? The work caused a change in kinetic energy. He recognized that his final kinetic energy was 0. Solve the thing for force. Voila, you're good to go. Very nice. It's an elegant solution. Okay, questions? We feeling good about that one? Okay, good. Good, good, good. All right, we want to do one more after that. That was a quick one.
I'm working.
You want to do one more? All right, choose one. Let me share my screen. I'll let you guys can pick which one you like. So on this page, we've got, let's see, all but the one we just did. If we go. On the first page, we've done, let's see, the 2 on the right, or the 2 on the left, sorry. And then on the last page, we've done the two on the bottom. So what floats your boat? What do you want to do?
On the middle slide, I think slide 5, could we do the top left one?
The top left one, the block on the inclined plane.
No, on my bad, the 4th slide.
So this one, car with a mass of 1,000 kilograms.
I swear I have a different.
How does it start?
Hold on. Never mind. It's the one of the like blob.
Ah, the
thing.
blob one. I was hoping somebody'd ask for that one because that one we can actually watch a video of. So a couple of years ago, I was at a lake and with my family, and one of my cousins brought this thing. Anybody ever seen one of these? Oh, they're a blast. Okay, so all this is a giant bag of air. It's a giant inflatable blob, right? And the really cool thing about it is that it is a fantastic way to launch people very high into the air. So what you do is you get a couple of people to come up here on this platform, and they jump off and land on the back of the blob, and that compresses the air in it, and you have somebody sitting on the front of the blob, and they just get shot off into the air. Okay, so let me play the movie, and you guys can watch. It's just a few frames, but you get an idea of what we're talking about here. Isn't that great? So this thing is a blast. And the really fun thing about it is it turns out it's actually a fairly gentle way to get launched violently into the air. Because the blob, right, when you're sitting on the front, you're sunk down a ways into it. So it's not like you get like just launched all at once. The blob like kind of accelerates you over the course of like, a few feet. So it's much gentler than you would imagine, right? You have this sort of gentle whoosh, and then you realize, my goodness, I'm like 25 feet in the air. The other fun thing about it we learned is that everyone, and I mean everyone's instinctual reaction to being launched off this thing is to wave their arms and legs like they're trying to do something, right? It's completely useless, but it's what everybody does. All right, so that's enough about that. Let's talk about the actual problem. Okay, so we've got 200-kilogram people who jump off of a 3-meter tower onto the back of a blob and launch a 50-kilogram person into the air. What's the maximum height the launched person can achieve? Okay, let me stop sharing my screen and we'll come over here and work this thing. So, does this system actually conserve energy? All right, we've got our blob. We've got people on a tower. And we've got a person over here. Okay, and they're going to get shot off into the air. Does this system actually conserve energy?
Yes.
Well, okay.
Mhm.
Well, let me be more careful with that. Where does the energy go? Right? Initially, you have potential energy, right? Gravitational potential energy up here. Does all of that gravitational potential energy go into this person?
No. Isn't some of it absorbed by the blob thing?
Yeah, so you guys, if you've had chemistry, you know that when you compress air, you heat it up, right? So when you jump on the blob and compress the air in the blob, some of that energy goes into heating up the air. Some of it goes into pushing the blob down into the water, which then makes waves on the surface of the water. Some of that energy goes into sound. This thing makes this wonderful kind of whoop, whoosh sound when you jump on it. Some of that energy goes into bouncing the people that jumped off of it back up, because they sink in a little too far and then they get pushed back up a little bit. There's a lot of places energy can go here. So what we're going to do is figure out the maximum case, right? Assume all the energy goes into the person. What's the highest it could possibly go? Okay, so initially we have potential energy up here, right? Gravitational potential energy, which is just going to be 2 people times their mass times 9.8 times their height, right? Which we know. We said their height is 3 meters. Okay. And then the highest this person could possibly go is if all of that potential energy goes into what?
Launching the person upwards.
Yeah. So in other words, kinetic energy, right? So all of it goes into some kinetic energy from this person, right? I don't know what I'm writing there, which is just 1/2 the mass of the, okay, so these are the heavy people, right? So I'm going to write those ones as big M, and I'm going to write the light person as mv squared. By the way, we did this one time with me and my brother-in-law, he weighs about 280, and we launched a cousin of mine who maybe weighs 100 pounds. It was fantastic. We launched her like halfway to the moon. It was beautiful. Okay, so goes into the kinetic energy of the person. And then where does it go? So the person has some kinetic energy, and then what happens to the person?
That all gets converted into potential energy.
Right. So
Again.
we're gonna be back to gravitational potential energy up here, which I'm gonna write as little m times g times big H. Okay, if I conserve energy all the way through, I don't even need to worry about this part, right? I can just go straight from here to here and say that the gravitational potential energy of the people on the towers is equal to the gravitational potential energy of the person at their highest point. Okay, if I set those two equal, I get little m g times big H equals 2 big M g little h. And the g's cancel. And so I get that big H is just 2 big M little h over little m. Or if I plug this in, right, that's 2 times 100 times 3 meters over 50, which 100 over 50 is just 2. So the answer is about 12 meters. So 12 meters is really high, right? That's almost 40 feet tall. We didn't get people that tall, even in sort of the most extreme cases we worked out, because you do lose a lot of energy over the process. But it's fun to ask, what's the worst case scenario, right? Because that way you know, okay, maybe I shouldn't do this because I'm going to kill somebody. Which we didn't, not even close. We had a good time. All right, so
Can I give it a try to one problem?
you bet. Go for it. Which one
So
do you want to do?
I did on slide 4 the coefficient of static friction
Okay.
on a plot.
Do you want me to show the problem?
All don't know if I could, if you could see my screen.
All right,
it's
so
gonna
hold
be
on.
hard to see.
Before you get there, you're talking about this problem. The coefficient of static friction between a block and an inclined plane is 2.0. What's the maximum angle to which the incline can be tilted before the block begins to slide? All right, so I'll
Yeah.
stop sharing and let you take
I
it
don't
away.
know. So I think I'm gonna talk about it because I don't know if you guys could see my work. It's hard, huh?
Yeah, it's a little tricky.
So can you guys see my free body? No?
I can see it.
Okay, I'm just gonna talk about it then. So I drew an incline, like a right triangle, and then I drew my block in the middle of it, and then I wrote theta at the bottom of the triangle, and I put mg as the vector going down. Can you guys hear me?
Yep.
Yeah.
Okay. So then I ended up with an equation that says mg, which is for friction. So then I substituted for friction mu times normal, which for my free body diagram, normal was equal to mg cosine theta. So once I got mg sine theta equals mu mg cosine theta, then I moved my sine theta and cosine theta to one side. The mg's canceled out. And so then I got sine theta over cosine theta equals the coefficient of static, which was 2.0. And then tangent theta equals 2.0. Then solving for theta would be tan inverse of theta equals tan inverse of 2.0. Then if you do that in your calculators, theta equals 63.43 degrees.
All right, questions.
I wish I could show you guys, but
So I
Uh-huh.
wrote it down as you were talking. Does that look right? Well, no, it looks horribly messy. Come on, thing, figure out your life. We're just not focusing today. There we go. Does that look right?
yeah, that's what I have.
Okay, so
for
you've
my
got.
free body, yep.
Go ahead.
I just have like a theta. So where normal is, just
Mhm.
like a line going straight down from there. Yep, like that.
And this,
And
and so
then
you
from-
said this is theta, which means this is
That-
theta, right?
Yep, that little theta right there.
Okay.
And then from there, I went and labeled it as that opposite side was mg sine theta.
Okay. So
That right
this
there.
piece is mg sine theta.
And then the other corner, the other side is mg cosine theta.
All right.
And then, yep, and then for friction is equal to mu times normal, which then I got mg. I don't have that on mine.
Okay. This was just so you said that the force that your normal force from your free body diagram was just
okay.
mg cosine theta.
Yeah. No, you're right then. Yeah. Yeah, force of friction is equal to mu times normal, which is equal to mu times mg cosine theta.
Okay.
And then I said mg sine theta is equal to mu times mg cosine theta because that's at that what that statement is saying is that's where they're gonna stay at equilibrium or like the maximum angle or something. before it
Right.
begins to
So
slide.
this is saying where gravity is balancing the friction force, right?
Right. And then after we pass that angle, we're gonna slide.
Right.
Okay.
Because after you pass that angle, right, as you increase the angle, sine is getting bigger and cosine is getting smaller. Right? So at some point, this side is going to have to get big enough that this side can't match it.
Yeah. So then we get to that statement where we just kind of solve, we put the thetas on one side, and then sine theta, cosine theta is tangent theta equals 2.0, and then we solve for theta using tan inverse. And that's our answer, 63.43 degrees.
Great. Questions? We feeling good about that? I feel good about that. That's a nice problem. Well done. Okay, so the trick here is recognizing that this is a problem with zero acceleration, right? And so what we want is for the forces here to all add up to zero. So Luis did the very sensible thing of tilting his coordinate system and then breaking up only one vector instead of having to break up two vectors, right? If you didn't tilt your coordinate system, you'd have an X and Y component for both friction and normal force. If you do tilt your coordinate system, you only have components for gravity. And voila. Okay, how are we feeling?
So do we get extra 5 points?
Yeah.
Oh, great.
All right. I think we'll call it there for today. Remember, I'll stick around after class, whatever that means, is over, and answer questions if people have questions on homework or whatever. And then remember, for Wednesday we've got a perusal reading due, so dig into that perusal reading.